Hello and welcome to the Wide World of Physics, where today we're looking at part 3 in our series on waves and their properties, and we are looking at a property called total internal reflection. Total internal reflection is the complete reflection of a ray of light within a medium such as water or glass from the surrounding surfaces back into the medium. The phenomenon occurs if the angle of incidence is greater than the certain limiting angle called the critical angle. This is somewhat more complicated than the first two parts to the video. It involves a bit of math that we can discuss, but more importantly, we can break it down into somewhat easier circumstances knowing two things. One, we can know what we're talking about by critical angle, and two, what this means in English. To start with, let's look at a graphical representation of what that just said. So as the light comes in, at a certain angle, it will get to a point where it will completely reflect off of the boundaries of the material itself. So if you have a glass block, for example, which I will show you in a moment, the glass block, at a certain angle, what you will see is that it will reflect up, reflect down, and reflect back up again. It's purely based on the fact that this boundary is greater, this angle that it's coming in, that boundary will provide too much of a reflection for it, and it won't want to go out, it will want to go back inward. There's some math behind that which we're going to look at now. So the equation that you're looking at, and I realize this goes beyond what some of you need for this, and if you would like to skip this part of the video, I fully understand. But how this works is you have n sine theta equal to 1. That's the key point, that it has to equal to 1. Okay? So sine theta, when you rearrange it, is 1 over n, where theta is the angle at which that light is coming in. So you have the sine of that angle coming in. N is your refractive index. Now your refractive index is literally just a number. It's a number that relates to the material specifically. So for glass, that number is 1.52. Okay? So to find the critical angle, all you would have to do is put 1 over 1.52, take the inverse sine of that, and you can find the angle at which glass will have a total internal reflection. You can do this with whatever material. You can either know the angle or know the refractive index of the material. It requires you to know one of those two pieces of information. You can't find both of them, I'm afraid. You can measure the angle to find the refractive index, or if you know the refractive index, you can then calculate the angle at which you need. But unfortunately, you do need a bit of that information. So, how would you do this? How would you see it? And where would you use it? Let's have a look. Now, as you see, this is a curved piece of perspex, but it shows exactly what I'm talking about quite well. As that light comes in, it doesn't come straight out the side. What happens is we're over the critical angle, so it bounces inward, bounces down here, and then makes another bounce and comes out the end of the tube over here. This is used in medicine, it's used in computers. We're going to talk about that in a moment. But that angle has been met and exceeded in order to bounce that light a couple of times. Let's look at it in a slightly different way. Now this is an hourglass shaped bit of plastic, and what you can see is we partially meet the conditions. So as the light comes in, it reflects internally, but what doesn't happen here is you can see it comes out, but it comes out dispersed. And it comes out dispersed because we haven't met the conditions on this side. So to have this happen, to have it bounce repeatedly, you need to meet the conditions on both sides. You need to have those conditions met always in order for this to work. If it meets it partly, you can get it to reflect a bit internally, and then it will refract, because you can see it comes out at a different angle that it goes in. So it does refract, it obeys the law of refraction, but it does not follow internal reflection because you cannot get it to bounce. It's just the wrong shape. The shape of the thing is important. Now where you see this quite often is in something called a fiber optic cable. You may see these in televisions or your stereo system. Computers use them quite often. They're used quite a bit of places. Where you don't know what's in it, it looks just like this black cable here. This black part of the cable is the outer coating. That's all you see from it. You don't actually see what's inside of it. Inside, there's this kind of white fibrous material. That's just a cladding to help protect the cable itself, and it's there to keep the cable from having any issues, because you want to have all of your information sent through this core. Now that core is made of either plastic, glass, or some kind of composite material that is designed purely to take your information and bounce it along the cable, all the way along that cable, in whatever angle it comes into, to then be received by the other piece of the puzzle. So if you have a DVD player that hooks into a stereo system, that will transmit the audio information from the TV, from the DVD player rather, into your stereo. You will shine a beam of light down one end of this. That beam of light will then be reflected internally into the cable itself, coming out all the way through the other end. Now the other place that these are used quite often is in something called an endoscope, which is in medical terms to basically, it's a scope that they will put down your throat, for example, and they can then see, because there's two cables on the inside of this, one that transmits light down and the other that has kind of a camera attached to the end of it, which will then take that information back. So there's two cables in an endoscope. It will then show you what's here on the end of the scope, and it will transmit that all the way back up your esophagus and out to a TV screen or some kind of monitor where the physician can see what's going on. But it's still the same information. You can actually, if your lens is good enough, you could actually look down that cable and see what is around the corner. They use this, the police are starting to use these, the military are starting to use them as kind of pinhole cameras that you can feed around a corner to see what's going on. Like the periscope idea, just a lot more modern version of it. Thank you for watching part 3 of our series. Please remember to like and subscribe to this channel, and please stay tuned for future content. Thank you very much.